Let's look at the stability of fixed points of higher dimensional linear maps, and to make our life notationally a little bit easier, let's take a look at a two-dimensional situation. So where we have a 2D map, where we have two inputs, x and y, and because it's a linear map, the output of that map is just given by the multiplication of a matrix A with the column vector x, y. So A is a bona fide matrix, A11, A12, A21, A22 times this column vector x, y. Okay, so these are the linear maps that we're looking at here. A question you might ask yourself, and pause the video and do ask yourself these questions, is like, what is the fixed point of this particular map, and how in general would you tackle the study of its stability? If you stare at these equations long enough, you will eventually realize that if you plug in 0, 0 for x and y, then you also end up with 0, 0 at the output. So the origin is the fixed point of this particular map over here. And to study the stability, we do the same thing we did in one dimension. We just look at the image of an epsilon neighborhood around the origin. And if you can find one where everything eventually maps down to the fixed point itself, you have a stable one. If it runs away in all directions, you have an unstable fixed point. And then, as we know from last video, you can also have a situation where you have a mixture of attracting and repelling directions, and then you have a saddle point. Okay, so let's try and do that. But before we actually do that, let's take a look at a situation where this 2D map actually behaves very similar to a 1D map, and therefore that simplifies our life a lot. So let's look at a situation where we don't look at a general initial condition, this vector xy, but rather we look at very specific vectors, namely, for example, a vector v0, which is an eigenvector of the matrix A with eigenvalue lambda. So pause the video, calculate the orbit of that initial vector, and see what happens. So let's calculate the orbit, and more specifically, let's calculate v1, which we get by having A operating upon v0. And simply because v0 is an eigenvector of A, we get that this is equal to lambda times v0. Okay, let's keep going. For v2, we have A times v1. v1, we just calculated that to be lambda v0. So lambda is just a scalar that can move in front of the matrix. So we have lambda times A operating on v0, but we just calculated that over here. This is again lambda v0. So in general, you can write that Vn will be lambda to the power of n v0. So this is a very specific case. And you see this is actually very reminiscent of a 1D map, because if you look at each of the coordinates of the x and y coordinate here of v0, that for each of these coordinates you can write down a linear 1D map, namely that, yeah, so how shall I write this down? So that you have, for example, kn plus 1 is equal to lambda kn. So this behaves in each of its coordinates as a 1D linear map. So this shows us that eigenvalues and eigenvectors, they will play an important role in our story, but it's still not really the complete picture, because here we looked at very specific initial conditions for our orbit. The question is now, what happens if we look at the more general case where the initial point can be arbitrary? But do eigenvectors then still play a role? The answer is yes, because you know, for example, from your kindergarten linear algebra classes, that if you have two eigenvalues, lambda 1 and lambda 2, which are different, that then in that case you can decompose your matrix A as a matrix Q times a diagonal matrix with the eigenvalues on the diagonal times the inverse of that matrix Q. And the matrix Q is a matrix which contains as its columns the different eigenvectors. Okay, so if we are in a situation like this, can you now pause the video and calculate explicitly the orbits of a general arbitrary initial condition for this map. Let's see what happens. So again, just like before, we have V1 being equal to A times V0, and then V2 being equal to A times V1. And that's actually, if you just plug in the previous equation into this equation, that's going to give us A squared V0. So for each of the different elements of that orbit, you need to raise this matrix here to a certain power. Now, because we have this particular form of this matrix, this actually simplifies the calculations a lot, because if you calculate, let's say, A squared, so this is going to be Q lambda 1, lambda 2, Q minus 1, and then we copy and paste, giving us Q lambda 1, lambda 2, Q inverse. And now something fun happens, is these guys over here, they cancel, they give you the unit matrix. And the product of these two diagonal matrices is also very easy to calculate. So in the end, you end up with something like Q lambda 1 squared, lambda 2 squared, Q minus 1. So this decomposition makes it very easy to raise matrices to arbitrary powers. And in general, you can keep on playing that game. You can write down that A to the power of n is lambda 1 to the power of n, lambda 2 to the power of n, Q minus 1. Right. So this gives us an explicit form of what will happen eventually to the orbit, because we're interested in what happens if n goes towards infinity. Pause the video and see what conclusions you can draw on stability if you look at the eigenvalues of this matrix here. First of all, if you are in a situation where the magnitude of these eigenvalues is strictly smaller than 1, if you then take the limit of n going towards infinity, the elements of this diagonal matrix here will go towards 0. This means that the orbit will end up in the origin again, which was our fixed point. In this case, means that we have a stable situation, we have a sink. Okay, so let's keep on playing that game here, and let's now look at what happens if the magnitude is bigger than 1. Now in this case, the important numbers over here, this diagonal, these numbers will go towards infinity. So our orbit will eventually completely run away from the fixed point, which is the origin. So here we have an unstable fixed point. This is a source. And then finally, you can have this mixed situation where you have one direction which is attracting and another direction which is repelling. And in that case, you can identify that you have a saddle point. So this tells you that the eigenvalues of the matrix really play a very important role in the stability of this linear system. You might wonder, okay, yeah, but this is true for the case where we said that lambda 1 and lambda 2 are different. Can you also generalize this when you have eigenvalues which are exactly the same? And then the answer is yes, and there's an exercise video on that particular topic that shows that also in that case the conclusion is the same. Obviously, if the eigenvalues are the same, you cannot have a saddle point in that case. Right, so here we have shown that eigenvalues are crucially important for linear systems and their stability.